Here we get to take a look at infinite sets. So far in the very first class, we just said that any set that's not finite is infinite. But we get to see a little bit of set theory here and some proofs. Okay, so a definition, an infinite set is a set that can be placed in a one-to-one correspondence with a proper subset of itself. So as long as we know the meanings of those words, then it's easy. So let's see as a reminder, right? We say an infinite set is a set that can be placed in a one-to-one correspondence. Well, remember, a one-to-one correspondence means that every one element in one set corresponds to one element in another set, and there's no elements left over in either set. Now, at the same time, we're creating a one-to-one correspondence with a proper subset of itself. Well, a proper subset means that there's fewer elements in one set than the other. So how could this be? How can we create a one-to-one correspondence with a proper subset of itself? Well, it's only when this can be done that we have an infinite set, because it cannot be done otherwise. Here I have an example. Set A contains the elements A, B, and C. And if we create a proper subset, right, that means we have fewer elements in this set. Well, if we try to create a one-to-one correspondence, we see that we have one element left over, right? Because we created another set, a subset, a proper subset that has fewer elements. Okay, so these are not infinite sets, right? These are finite sets. Well, let's prove this with infinite sets. Right, here we can see that set A is not an infinite set. Okay, so the question says, show that the following sets are infinite, and I tell you how to do this. By placing it in a one-to-one correspondence with a proper subset of itself. But we have to do this for every element in the set. So when we look at example A, we can see that the first element is 2, the second term, right, is 4, the third term is 6, the fourth term is 8, the fifth term is 10, right, the sixth term is 12. And we say, well, how do we know this? You see, we keep adding 2 to get to the next term. So first term is 2, second term is 4, third term is 6, fourth term is 8, right? Fifth term is 10. We say, well, do we know what the 10th term is? Right? The 10th term is going to be 20. Because notice we keep adding 2, right? First term is 2, second term is 4, third term is 6, fourth term is 8, 10th term is 20. Here, what would the 100th term be? Right, that would be 200. You don't have to write it all out, right? Fifth term is 10, sixth term is 12, seventh term is 14. It's always times 2. Right? 1 times 2, 2 times 2, 3 times 2, 4 times 2, 10 times 2, 100 times 2. So we know what every term is. So in general, for the nth term, n could be any number. You want to know what any term is, say the nth term. The nth term. Well, it's just going to be 2n, 2 times n. And another way of seeing this is that whatever the difference is between each of the terms, the difference is 2. We go from 4 to 6, the difference is 2. From 6 to 8, the difference is 2. Whatever this difference is, 2, that's always going to be the number in front of n, because these are multiples of 2. If we have 2 once, 2 twice, right, second term, 2 3 times, third term, 2 4 times, right, fourth term, 2 5 times, right, the fifth term, we get 10. So 2n times is going to be 2 times n. All right, so we know what every term is in this sequence. Right, first term, second term, third term, fourth term, right, fifth term is 10, the nth term for any number n. Alrighty, so what we're trying to do is, right, we don't want to forget, we want to show that the following set is infinite. How? We place it in a one-to-one correspondence with a proper subset of itself. All right, so in order to create a proper subset, I'm just going to get rid of the first term, 2. There we go. I'm going to start with 4. Now I know that this right here is a proper subset, right? Because it has fewer terms. I took out the first term. I took out the 2. Okay, well, notice when we go from the first term here to the first term here, right, we're adding 2. When we go from the second term, 4 to 6, we're adding 2. We're going from the third term, 6 to 8, we're adding 2. We go from the fourth term, 8 to 10, we're adding 2. So that's going to be our correspondence. 2n is going to correspond, we add 2, to 2n plus 2. And we're done. We have just shown that the following set is infinite. How? Because we placed it in a one-to-one correspondence with a proper subset of itself. We took out the first term, and we're still able to create this one-to-one correspondence, and there's no terms left over in either set. It's got to be infinite. We're done. Okay, in example B, right, the first term is 3, second term is 6, third term is 9, fourth term is 12, right? The fifth term is 15, right? Because we keep adding 3. So notice the first term, 1 times 3, second term, 2 times 3, third term, 3 times 3, fourth term, 4 times 3. Whatever the difference is, right? We're adding 3, adding 3. Whatever that number is that we're adding 3. That's always going to be the number in front of n, because now we have multiples of 3, right? So if n is 2, we have the second term, right? If n is 2, 1, 2, right? 3. If n is 4, the fourth term, we have 3 times 4. We have the 12th term. If we want to know the 100th term, it's 3 times 100. It's 300. So we know what every term is in this sequence. Okay, so now to show that this set is infinite, what we're going to do is, and I tell you in the directions, we place it in a one-to-one correspondence with a proper subset of itself. So I take out the first term, right, and I start with 6. So now this set right here has fewer elements in it because I took out the 3. And I ask myself, well, I'm creating a one-to-one correspondence. This first term 3, in order to get to 6, we add 3. The second term 6, we add 3, we get 9. The third term, we add 3, we get 12. The fourth term, we add 3, right? 12 plus 3, we get 15. So to go from each term in this first set to each term in this second set, we're adding 3 to each term. And we do that likewise here, 3n plus 3, and the 3n will correspond to 3n plus 3, and we're done. We have just shown that this is an infinite set. Why? We created a one-to-one correspondence. There's no elements left over in either set, even though we took out the first term, and the second set right here starts with 6. There's fewer elements in this set. Okay, so we've shown that it's an infinite set. Okay, the next 3 examples are kind of interesting. C And you should try doing these on your own first, before you see my explanation. But C is pretty straightforward. We see the first term is 5, the second term is 10, the third term is 15, fourth term is 20, right? The next term, the fifth term, is going to be 25, right? We keep adding 5, right? We add 5, we add 5. And so because we keep adding 5, we know, right, the nth term is going to be 5n. Whatever the difference is between each of these terms, right? We add 5, right? We add 5, we add 5. Whatever number that is, that's always going to be this number right here in front of the n. Okay, now to show that this set is infinite, okay, what we're going to do is we're going to place it in a one-to-one correspondence with a proper subset of itself. So we're going to take away this first term right here, that 5, and I'm going to start with 10. So now there's less elements in this set than in this set. I took out the 5. Okay. And to create that one-to-one correspondence, to go from 5 to 10, right, we add 5. To go from 10 to 15, we add 5. To go from 15 to 20, add 5. To go from 20 to 25, add 5. And so we're creating this one-to-one correspondence. To go from 5n, right, we're going to add 5, and we go to 5n plus 5. And we're done. We've shown that this is an infinite set right here. This is an infinite set. Why? Because we created a proper subset right here. We took out the first term, and we created a one-to-one correspondence, and there's no elements left over. And we're going to do the same on D and E. But be careful here. See, first term is 8, second term is 13, third term is 18, fourth term is 23. What would the fifth term be? You see, we keep adding 5. We add 5, we add 5, we add 5. And so the next term would be 28. 28. Because we're adding 5. Which means that this number in front of n is going to be 5. Now, so far we've had even multiples. We had our multiples of 2, 2, 4, 6, 8, 10. We've had our multiples of 3, 3, 6, 12. Here we have our multiples of 5, 5, 10, 15, 20. Okay, the trouble is we are not starting with 5 here in example D, right? We're starting on 8. So when n is 1, the first term is not 5, the first term is 8. So in order to start on 8, we have to add 3. So now the first term, n is 1, we get 5 plus 3. When n is 2, right? 5 times 2, that's 10, plus 3, we get 13. When n is 3 for the third term, 5 times 3 is 15, plus 3, right? Third term, we get 18. And you see, so whatever term we're on, n is the number of term we're on, that'll tell us what place we are in the sequence. It'll give us every term in the sequence, in other words. Okay, so now that we know that, to show that this set is infinite, we place it in a one-to-one correspondence with a proper subset of itself. So I'm going to take out the 8. I'm going to start on 13, right? So now there's less elements. There's fewer terms in this second set. I took out the 8. So to create this one-to-one correspondence, we go from 8 to 13, we add 5. To go from 13 to 18, we add 5. To go from 18 to 23, we add 5. To go from 23 to 28, we add 5. And we're going to do the same thing with 5n plus 3. We're going to add 5 to get its corresponding term. And we get 5n plus 3 plus 5. We get 5n plus 8. And we're done. We've shown that this set right here is an infinite set because we took out one of the terms. We're starting on 13. And we created a one-to-one correspondence. And there's no terms left over. Okay, we'll do the same on E. Okay, show the following sets are infinite. How? By placing it in a one-to-one correspondence with a proper subset of itself. Okay, so we have to find the nth term. We have to. We know the first term is 8. First term is 5. Second term is 8. Third term is 11. That's a 3. Third term is 11. Fourth term is 14, right? What is the fifth term? Well, we see we keep adding 3, add 3, add 3, add 3. To get to the next term, we still add 3, 14 and 3. We get 17. So whatever number we keep adding, the 3, that's going to be the number in front of the n because we have multiples of 3. Okay, the only problem is we're not starting on 3. We're starting on 5. But when n is 1, we get 3. In order to start on 5, we have to add 2. So when n is 1, we get 3 times 1. That's 3 plus 2. When n is 2, we should get 8. When n is 2, we get 3 times 2, right, which is 6 plus 2. We get 8. When n is 3, right, we get 3 times 3 is 9 plus 2. Yep, we get 11. And so that checks. Okay, now to show that this is an infinite set, we place this in a one-to-one correspondence with a proper subset of itself. Okay, so a proper subset, we get rid of that first term. We start on 8. Right, so this way there's fewer elements in this set right here. We took out the 5. And to show that we can create a one-to-one correspondence, when we go from 5 to 8, we add 3. To go from 8 to 11, add 3. 11 to 14, add 3. 14 to 17, add 3. And we do the same to find what 3n plus 2 corresponds with. We add 3, and we get 3n plus 2 plus 3, which means we get 3n plus 5. And we're done. We've shown that this set right here is an infinite set. We placed it in a one-to-one correspondence with a proper subset of itself. Okay, I have one last example here I'd like to show you with fractions. Oh, let's see, before we get to that. Oh, I got another definition too. Alrighty, here are some things that we know. Okay, the cardinal number of set A, the number of elements in set A, right? There's 3 elements in set A. So the number of elements in set A is 3. Cardinal number of set B, the number of elements in set B, right? There's 1, 2. 2 elements in set B, right? No braces, right? Braces means it's a set. Now we're just counting the number of elements. Well, we run into a little bit of trouble here trying to find the cardinal number of set C. That is the number of elements in set C, right? Because it's an infinite set, right? It never ends. You say there is no last number to say what is the number of elements in the set. It's an infinite set. So what George Cantor did here was, remember, he made this up. Okay, so he wanted to give this a name, and he could have named it anything he wanted. I mean, he made it up. And so he decided to call it the first letter of the Hebrew language, Aleph, with a subscript of 0 underneath it, a 0. And the way we say this in math is Aleph, null, Aleph, null. And so if you want to know the cardinal number of an infinite set like this, it would be Aleph, null. Okay, I tell you this because of the next definition. Okay, we need to know what this means. Okay, and remember, this set is countable. We know exactly what every element is, right? The first term is 1, second term is 2, third term is 3, fourth term is 4, fifth term is 5, right? The 57th term is 57, the nth term is n. Okay, so it is countable. We know exactly what every term is. Okay, that's what it means when we say it is countable. Okay, here, a definition. Any set that can be placed in a one-to-one correspondence with a set of counting numbers. Okay, now we're not dealing with subsets of a set, but it's a one-to-one correspondence with a set of counting numbers. Okay, we say has cardinality Aleph null and is countable. So in this example, I'm saying show that the following sets have cardinality Aleph null. And I tell you how to do this. How do you do this? By establishing a one-to-one correspondence between the set of counting numbers and this set. We set a one-to-one correspondence. Okay, so in order to do that, right, we know the first term is 2, second term is 4, third term is 6, fourth term is 8, right, fifth term is 10. And we can see, right, we keep adding 2 to get to the next term. We keep adding 2. So we know that 2 is the number in front of n, right? We want to know the first term, n is 1, we get 2. To know the second term, n is 2, right? N is 2, we get 2 times 2, we get 4. And when n is 3, the third term, n is 3, the third term, we get 2 times 3, we get 6. Okay, so we know what every term is. Okay, now to show that this set has cardinality Aleph null, I tell you how to do it. We establish a one-to-one correspondence with the set of counting numbers, always. So to set this one-to-one correspondence right here, we're done. First term is 1, second term is 2, third term is 3, fourth term is 4, nth term is n. We have our one-to-one correspondence, we're done. Okay, we do the same here in this next example. Right, first term is 3, second term is 6, that's a 2. Third term is 9, fourth term is 12, right? Fifth term, 15, right? Because we keep adding 3. Add 3, add 3. Here we add 3, add 3, add 3, right? 12 plus 3, we get 15, we add 3. And so because we keep adding 3's, then the number in front of the n is 3. So to show that this set has cardinality Aleph null, we establish a one-to-one correspondence with a set of counting numbers. One-to-one correspondence, and we're done. It has cardinality Aleph null. And it is countable. Don't want to make more out of this, right? These are the same examples we just saw with the last definition, but we're asked a different question. We want to create a one-to-one correspondence with the set of counting numbers. Here, I have 3 more examples here, and you should try these before I go through them and see how you do. And then you could, check your work with what I have here. C is pretty straightforward, right? First term is 5, second term is 10, third term is 15, fourth term is 20, fifth term is 25. right? And we can see we keep adding 5, right, to get to the next term. That's how we get to the 25 for our fifth term. So we keep adding 5, right? And because we keep adding 5 to get to the next term, right, they're multiples of 5, we know that 5 is the number in front of n, the multiples of 5. So to show that this set has cardinality aleph null, and again, I tell you how to do this, okay, you establish a one-to-one correspondence, right, with the set of counting numbers and this set. So we have our counting numbers, right, 1, 2, 3, 4, all the way on, continuing on, right? First term is 1, second term is 2, third term is 3, fourth term is 4, fifth term is 5, sixth term is 6, nth term is going to be n. And we just create that one-to-one correspondence, and we're done. Okay. In example D, right, first term is 8, second term is 13, third term is 18, fourth term is 23, right? And the fifth term is 28, right? Because we keep adding 5, adding 5, adding 5, adding 5, and we add 5 to get to the next term, 28. So whatever number we keep adding to get to the next term, that's always going to be the number in front of n. So we have 5n. Right? The trouble is, right, we're not starting on 5, right? When n is 1, when first term, n is 1, 5 times 1, we're starting on 8. So in order to start on 8, we have to add 3, right? 5 plus 3 is 8. Right? And it'll continue on, right? To get to the second term, right? N is 2. It's 5 times 2. That's 10 plus 3. We get 13. Okay, so now that we know what every term is, to show that this set has cardinality aleph null, we establish a one-to-one correspondence between the set of counting numbers and the given set. So we just write down the set of counting numbers, create a one-to-one correspondence, and we're done. And notice these are the same sets as the previous definition. If you go back to problems A, B, and C, okay, we're just asked a different question. In example E, to show that this set has cardinality aleph null, right? Notice we have the first term, second term, third term, fourth term is 14, right? What is the fifth term? Right? We keep adding 3, add 3, add 3, add 3, and we see the next term, we also add 3. Fifth term is going to be 17. So whatever number we keep adding, that's always going to be the number in front of n. The trouble is, we keep adding 3 to get to the next term, but our first term is not 3, right? When n is 1, first term, when n is 1, you get 3 times 1, that's 3. We want to start on 5, so we have to add 2. This way we start on 5. Okay, then we add 3 to get to the next term, and add 3 and add 3. And that's really the hardest part, because from here we want to show the following set has cardinality aleph null. How? We establish a one-to-one correspondence between the set of counting numbers and this set. So we write down our set of counting numbers, create a one-to-one correspondence, and we're done. Okay, I'd like to show you an example with fractions. Don't want to be intimidated by these. Try doing this first on your own before you see me solving it. And we want to see the pattern. You see, Same question, show that the following set has cardinality L if null. How? By establishing a one-to-one correspondence between the set of counting numbers and the given set. Well, the first term is 1, right, or 1 over 1. Second term is 1 over 2. Third term is 1 over 3. Fourth term is 1 over 4. Fifth term is 1 over 5. Sixth term is 1 over 6, right? Seventh term is 1 over 7. Eighth term is 1 over 8. The nth term is going to be 1 over n. And it's really that easy. And so to show this set has cardinality L if null, we establish a one-to-one correspondence with the set of counting numbers, and we're done. So I hope this doesn't seem too bad and is much easier than it may have first seemed. And that's really all we're going to talk about in our introduction for set theory.